Now that we have all our connection 1 forms lined up, it's time to go ahead and calculate the curvature 2 forms. Note that we do not bother with the torsion forms here for the simple reason that this is Riemannian geometry and we know that all the torsion terms are simply 0. The basic equation that we need to use is the following. Rij is the exterior derivative of gamma ij plus the sum of wedge products gamma ik wedge gamma kj. And let me just remind you, in case you have forgotten, that the way in which you can calculate the exterior derivative of a form is very, very simple, especially when it's expressed in terms of the coordinate basis, because in general, if you have a form of ijk dot dxi wedge dxj wedge dxk dot, what you need to do is simply partially differentiate del fijk dot. These are just functions, so their exterior derivative is the same as a standard partial derivative, not really partial, total derivative. So del x, let's say alpha, then you put in dx alpha. I just wrote alpha to differentiate it from all these Latin indices we have put in. Remember, this is the dummy index, so we should not confuse it with any of the other indices that you are already using. And this is exactly the result that you are looking for. So, in the coordinate basis, calculating exterior derivatives is really rather easy. Now with this, what we will do is now calculate the curvature 2 forms one by one. So let's start with R11. For this, what you need is to calculate d gamma 11 plus gamma 1k gamma k1. So that's really a situation where these two indices are going to be 1 and this is going to be summed over. So it's going to be 1 1 gamma 1 2 with gamma 2 1 plus gamma 1 3 with gamma 3 1. And now, this may look like a difficult thing to differentiate, at least in your head, but you don't have to. Remember, this depends only on R. So when you differentiate this, the d of this function will only have a dr, and dr which dr is 0. So this is going to give you 0. Well, gamma 1 1 which gamma 1 1 is always going to give you 0. The wedge product between two 1 forms is always anticommutative, and so the wedge product of a 1 form with itself is definitely going to be 0. At this point, let me just remind you that a wedge product is not in general anticommutative. It's anticommutative when it's done between two R and R prime forms where R and R prime are both odd. In this case, of course, 1 forms, so anticommutative. Gamma 1 2 with gamma 2 1. This is gamma 1 2, this is gamma 2 1. No need to calculate anything. D theta with d theta will give you 0. And gamma 1 3 with gamma 3 1. Gamma 1 3, gamma 3 1, d phi with d phi will give you 0 again. So this one is actually pretty straightforward. All the terms here are 0. So curly R11 is 0. What about 1 2? That's d gamma 1 2 plus, okay, let me just work them out one by one as I go along. The d gamma 1 2. Now you're not going to get 0. What you're going to get is the derivative of this term, that's minus within bracket r minus kr cube. So minus 1 minus 3kr square dr wedge d theta. That's d gamma 1 2. Well, the rest are going to be very similar to this, except that this index here is going to be replaced by 2. So we have gamma 1 1 wedge gamma 1 2. Let's take a look at that. This with this. Not a 0 because you have dr wedge d theta. And you cancel out the 1 minus kr square here. You have minus kr square dr wedge d theta. What about gamma 1 2 wedge gamma 2 2? That's the next term. Gamma 1 2 wedge gamma 2 2 here. Of course, as I said, this one has to be replaced by 2 for this calculation. So gamma 1 2 wedge gamma 2 2, again not 0. what you have is minus 1 minus kr square, but with a d theta wedge dr. This order is important, remember. Wedge products between one forms are anti-commuting. So the order is going to be very important. And the final term is going to be wedge of gamma 1, 3 with gamma 3, 2. Gamma 1, 3 is up here. Gamma 3, 2 is down here. Sine square theta times cot theta. Well, you don't even have to bother about that because d phi, you're going to get a 0. These are the only terms that you need to worry about. And they nearly cancel, except that they don't, at least not completely. You have plus 3 kr square dr wedge d theta. What you have is minus kr square dr wedge d theta, and this is plus 1 minus kr square dr wedge d theta. So the minus 1 here cancels with the plus 1, almost everything cancels, but you're left with kr square dr wedge d theta. So that's your R12. Pretty straightforward. What about R13? D gamma 13, that's actually going to be a bit longer. You're going to have to differentiate this. So now you're going to get two terms. One is going to be minus 1 minus 3k r square sine square theta dr wedge d phi. Just like in the previous case, except that you have a d phi here. And another term that you're going to get is minus r into 1 minus k r square. The sine square theta gives you twice sine theta cosine theta d theta wedge d phi. But that's just from the d gamma 13. What we need to do is you have to add to this gamma 11 wedge gamma 13, which actually is not 0. It's going to be the product of these two. The 1 minus kr square will cancel. You're going to get minus. Okay, let's get rid of this and just write it down. We have to be careful about the signs. So minus kr square sine square theta dr wedge d phi. The order also matters, remember. So dr from gamma 11, d phi from gamma 13. So gamma 12, gamma 23, that comes next. Gamma 12, gamma 23. And now you have this whole thing multiplied together. So you have minus r into 1 minus kr square times sine theta cosine theta well, two minuses make a plus, so, and you are going to get d theta wedge d phi in that order. That's a gamma 12 wedge gamma 23. You have one more term, gamma 13 wedge gamma 33. And gamma 13 has a d phi, gamma 33 has both. So let's write it out first. Minus r 1 minus kr square sine square theta d phi wedged with dr by r plus cot theta d theta. So there are quite a lot of terms apparently, but you should be able to see that most of these terms actually tend to cancel. Well, you have this and this, which of course almost cancel, but there's a minus 2 here and plus 1 here. But note, sine square theta times cotangent theta is actually sine theta cosine theta, the same factor as you have here. And this is d phi wedge d theta. So when you convert that to d theta wedge d phi, this becomes a plus. So this term, this term, this term, the three cancel out. What about the other case? Well, here note the r has cancelled with the r. So once again you have a situation where you have 1 minus 3k r square sine square theta extra here as opposed to the previous calculation, but essentially everything else is the same. dr wedge d phi. Here you have plus 1 minus kr square sine square theta dr wedge d phi again. So the ones cancel. You are left with minus plus 2kr square sine square theta from here. But one term cancels. So you are ending up with something very similar to the previous one, except for an extra sine square theta. dr wedge d phi. And that's the only term that you have in R1. So R11, R12, R13 are done. What about the rest? Now, just so that I don't move too far away from my gammas, let's move the R's that we have already calculated down. Let's go on and quickly calculate the R's. Let's just use a different color for this. R21, d gamma 21 minus 1 by R square dr wedge d theta plus gamma 21 wedge gamma 11. That's gamma 21 wedge gamma 11 k by 1 minus kr square d theta wedge dr. You have to be careful, as I said, about the order. Plus gamma 22 wedge gamma 21. Gamma 22 wedge gamma 21. That's plus 1 by r square dr wedge d theta. Of course, that gets rid of this term. And gamma 23 wedge gamma 31. So gamma 23 is this, gamma 31 is this. D phi's, they just cancel each other out. So d phi's give you 0, of course, d phi wedge d phi, and you are landing up with k by 1 minus kr square d theta wedge dr. You would like to change that order, perhaps, because I want it in 1-2 order. So minus k by 1 minus kr square dr wedge d theta. So now let's go in for R22. D gamma 22, that's 0. Minus 1 by r square dr wedge dr, that's 0. Gamma 21 wedge gamma 12. So this is gamma 21, gamma 12, d theta wedge d theta gives you 0. Gamma 22 wedge gamma 22 is obviously 0. Gamma 23 wedge gamma 32. This is gamma 23 with a d phi, gamma 32 with a d phi. Everything goes away. So curly R22 is simply 0. So we don't have to bother about this one. Let's just list the non-zero ones from now on. Then you have curly R23. D gamma 23, of course, differentiating the whole thing. This is minus half of sine 2 theta. So that's differentiate pretty easily to give you minus cosine 2 theta. Or sine square theta minus cosine square theta. D theta wedge d phi. That's just d gamma 23. To this you have to add gamma 21 wedge gamma 13. So gamma 21, gamma 13 minus, so this is a minus 1 minus kr square sine square theta d theta wedge d phi. Then you have to add to this gamma 22 wedge gamma 23. So gamma 22 wedge gamma 23. That gives you minus 1 by r sine theta cosine theta dr wedge d phi. Finally, you have gamma 23 wedge gamma 33. So minus, again a minus. Sine theta cosine theta d phi wedged with 1 by r dr plus cot theta d theta. The dr wedge d phi term is pretty easy to identify here. You have a minus 1 by r sine theta cosine theta as a coefficient here. Here you have minus sine theta cosine theta by 1 by r as a quotient once again, but you have dr which d phi in one and d phi which dr in the other. So these two terms just cancel each other out. What about this? Well, here you have sine square theta minus cosine square theta, and here you have minus sine theta cosine theta into cot theta. That of course is minus cos square theta, but becomes plus cos square theta because of the switch in d theta d phi order. So that gets rid of this term. So now you have sine square theta d phi left, d theta wedge d phi, and here you have minus 1 plus k r square sine square theta d theta d phi. So the minus 1 sine square theta cancels with this one, and you are left with k r square sine square theta d theta wedge d phi. So that's your other non-zero curvature connection. We still have some work to do and a lot of space here. So let's just move this whole thing down. This bracket had come loose, so let's just put that back. Now let's go in for the curly r's with 3 on top. D gamma 3 1 minus 1 by r square dr wedge d phi plus gamma 3 1 wedge gamma 1 1, product of these two terms, wedge product of course, k by 1 minus k r square d phi wedge dr. Remember it's gamma 3 1 wedge gamma 1 1. Then you have gamma 3 2 wedge gamma 2 1. This with this. So cotangent theta by r d phi wedge d theta. Finally gamma 3 3 dr by r plus cotangent theta d theta wedged with gamma 3 1 1 by r d phi. Once again we expect quite a lot of cancellations, and there are a lot of cancellations. You see 1 by r square dr wedge d phi. There's a minus sign. Here you have plus 1 by r square dr wedge d phi. So this one cancels. Cot theta by r d phi wedge d theta and cot theta by r d theta wedge d phi. They also cancel. So all you have left with is k by 1 minus k r square, the minus sign dr wedge d phi. That's your curly r 3 1. Let me just move things around a bit. Again to make space more than anything else. And you now have to calculate curly r 3 2. Well, d gamma 3 2 minus cosec squared theta d theta wedge d phi plus gamma 3 1 wedge gamma 1 2. Gamma 3 1 gamma 1 2, that's minus 1 minus k r square 1 by r and d phi wedge d theta. Then you have to add to this gamma 3 2 wedge gamma 2 2. Cot theta d phi 1 by r dr. Cotangent theta by r d phi wedge dr. And finally gamma 3 3 gamma 3 2. So cot theta d theta plus dr by r, that's the gamma 3 3, wedged with gamma 3 2 cot theta d phi. Okay, now what about the d phi wedge dr term? Cot theta by r in front here, cot theta by r in front here with the reverse order for the wedge products, so this term goes away. This is cot square theta minus cosec square theta. D theta wedge d phi. And that of course gives you minus 1 times d theta wedge d phi. This one on the other hand is plus 1 minus kr square d theta wedge d phi. So this is minus kr square d theta wedge d phi. So we have made some space for our final one, that's curly R33. D gamma 33. Well, despite the fact that gamma 33 looks a bit more complicated than the other terms, this has a zero exterior derivative, as it's very easy to see. So all you are left with are the wedge terms. Gamma 31, wedge gamma 13. Gamma 31 has a d phi, gamma 13 also the d phi, 0. Gamma 32, wedge gamma 23. Gamma 32, d phi, gamma 23, d phi, another 1. So again 0. Finally, gamma 33 wedge gamma 33 of course 0, so this term is 0. And now we are done with our calculation of curvature 2 forms. Our calculation is actually complete here. We have calculated all the curvature 2 forms, which has all the information you need about the curvature of this particular space. The non-zero curvature 2 forms that we have calculated have been listed here. And if you want, you can immediately read off the Riemann-Christoffel curvature tensor components from this. Let me remind you, the definition of Rij, these curvature 2 forms, essentially had half Rij KL, theta k, wedge theta L. So, for example, if you want to figure out R12, 1, 2, you just have to look at this. Actually, R12, 1, 2 and R12, 2, 1 both can be read off from this. Of course, these are actually negatives of each other. And you can immediately read out that the value for both of them, R12, 1, 2 on the one hand and minus R12, 2, 1 on the other, is given by kr square. Don't worry about this extra factor of half here. When you put both of these together and try to calculate curly R12, for example, what you will get is R12, 1, 2 theta 1 wedge theta 2 with a half plus half of R12, 2, 1 theta 2 wedge theta 1. Of course, the KLs are summed over all possible values, but these are the only 2 non-zero terms that we are getting here. And this is going to be give you a half kr squared theta 1 wedge theta 2 plus half of minus kr squared theta 2 wedge theta 1. And note that these 2 terms are actually equal to each other, cancelling out the half and giving us back kr squared dr wedge d theta. Now, what about R13, 1, 3 and minus R13, 3, 1? They are of course given by kr squared sine squared theta. You can immediately read off these terms. Okay, let's just get rid of this part of the calculation here and write down other Riemann-Christoffel curvature tensor components. R 2, 1, 1, 2 is minus R 2, 1, 2, 1 and they are given by minus k by 1 minus kr square. R 2, 3, 2, 3 minus R 2, 3, 2 is given by kr square sine square theta. R 3, 1, 1, 3 minus R 3, 1, 3, 1 is minus k by 1 minus kr square. Finally, R 3, 2, 2, 3 minus R 3, 2, 3, 2 is given by minus kr square. All the non-zero curvature tensor components have just been listed. It's just these 1, 2, 3, 4, 5, 6 independent components which are non-zero. Of course, 12 components are non-zero, but 6 of them are related by this antisymmetry. of the last two indices to each other. So 6 of these are independent, the other 6 follow from that. So our curvature tensor calculation is complete. Now this may seem like a rather long calculation, but I would just urge you to try to do it using the equations which relate the R components with the gammas, and you will see exactly how much simpler this is. In fact, this is not even the simplest thing that you can do. Very often, a simpler thing would be to use a different basis, not a coordinate basis, which makes life somewhat complicated to begin with, but actually makes it simpler in the long run. So let us take a look at the basic idea behind how to use a specific kind of basis called the rigid basis next, and try to do the same calculation using rigid basis. The pain that you will have to endure in learning about rigid basis and how the formulas change for that will be well compensated for by the ease of calculation that rigid basis will bring in.